Hello everyone. I'm very happy to be here in Singapore. And in my topic, I will talk about something about NVIDIA's Tegra platform. Let me introduce myself. I'm a member of Trend Micro Zero-Day Discovery team. I got rank 1 of Google Android VIP last year, and I also discovered some zero-day attacks in the wild in 2015. My research interests are Android, Flash Player, OS X, and iOS. Tegra is a system-on-a-chip series developed by NVidia for mobile device. NVIDIA announced that Tegra platforms are the world's fastest mobile processors. There are many smart devices using Tegra platform, like Google Nexus 9, Google Pixel 3, and Chromebooks. There are also many car brands using Tegra platform, like Tesla, Rolls-Royce, Bentley, and BMW. So Tegra platform's security quality has widely impact on our daily lives. Finding and patching Tegra's vulnerability is worth to do. I only had one Nexus 9 in my hand when I began to do research on Tegra platform. Google Nexus 9 was released on November 2014. It is a tablet co-developed by HTC and Google. Nexus 9 is using Tegra K1 platform. I found some kernel mode bugs of it and wrote exploits for these bugs. So I will introduce some of these bugs and one interesting exploit. I found these bugs by code audit. You can download and build kernel of Nexus device. Google has a very good guide for. You can add your debug information into the kernel source and build your own debug kernel image. Personally, I like to use SourceInsight as a code audit tool. Usually, you can audit the code from attack surface to the kernel. There are some typical attack surfaces, such as device nodes and sysfs, procfs, and system code. When you find suspicious bugs, you can construct a POC and use your own debug kernel image to debug the POC. You can get the kernel panic information on this folder, data system job box. There are some bug examples I found. The first one, it's in driver NVhost control when handling one IO control command. We can see that this driver can be accessed by any user. And in the source code, there is an integral flow when kmalloc a buffer. The number of sets and the block size are input from user space. The multiplication can cause the integral flow. And the integral flow will cause kmalloc to allocate a smaller buffer than we want. This is the second example. It is in driver NVhost GPU when handling one IO control command. This driver also can be accessed by any user. You can see in the code, the argus offset. The code doesn't check the argus offset. So if we input a data value, the memory set will write 16 bytes 0 to an unknown address. But if we can leak the VA, the value of VA, we can write 16 bytes 0 to an controlled kernel address. This bug is in the camera driver. Camera driver can be accessed in the media server process. It needs a privilege, media or camera. This bug is a risk condition bug. You can see the source. When handling one IO control command, the mutex, the scope of the mutex is not very good. The lock doesn't protect the camera remote device, so it can cause user apt free. Allow me to do some advertisement for Google. Google started Android vulnerability reward program at June 2015. It now rewards 64-bit Nexus device, rewards bugs of 64-bit Nexus device. Taking the 3 bugs above, for example, you can get $40,000 US if you are the first reporter and submitted 3 root exploits. Okay, now I will try to exploit the first bug, the integer overflow bug. So what we get after first glance? The vulnerable function is to read and write a module register. And each time you read and write the register, you can specify one offset and byte count to operate. The argues block size is the byte count to operate. It should not be a very big value to avoid crash. But if you want to overflow the multiplication, the number offset must be a very big value. So let's check the code deeply. When the argues write is true, because we know argues is controlled, can be controlled by us in user space. So we can set argues to true. The execution, this means it will write to a register. So the execution flow is like this. Kmalloc a buffer and copy from user to fill the buffer. Then enter into a while loop. Each time read an offset from user space by calling getUser, read an offset, and then call the MV host write module regs to write the buffer content to the register. When writing, you can specify an offset read out from user base, and the remaining is the block size. So the block size is the count. So we can set block size to 4. Means each time write 4 bytes to register. So number of offsets should be a normal value, because we don't want an integer overflow when we write to register. This is the function write to register. The execution flow is this. The first validate reg to validate the input offset and the byte count to write. If the offset and the count are validated. Then write the values to the register. The values is from the kmalloc buffer. When the argues write is false, there is another branch, else branch. The execution flow is similar with argues write is true. In the while loop, we get an offset from user space by calling getUser, and then call NVhost read module register to read from register, and then write the values to the kmalloc buffer. So in this branch, we have a chance to overwrite the kmalloc buffer. So we can set the block size to 4. Means each time read 4 bytes from register and write them to kmalloc buffer. This time, number of offsets should be a very big value because we want to make integral flow. When integral flow, kmalloc will allocate a smaller buffer to be overwritten. So if number of offsets is a very big value, the while loop in the code will be a huge loop, almost infinite. You can see while offset. So if number of offset is a very big value, the while loop is almost infinite. This is the read from function of read from register, NVhost read module register. You can see the execution flow is similar with the write. Validate the register, validate the offset and the count first. If the offset and the count are valid, then read from the register and write to the buffer. So we must solve the infinite loop problem if we want to overwrite the kmalloc buffer. We can take a look at the validated reg function. In the validated reg function, it will check the offset and the count are bigger than resource size or not. And it will also check if the offset and the count will cause integral flow or not. So if we set the offset to a very big value, it will cause the check fail and it will return error. When validated reg return error, we can see that read module regs will return error. And the while loop, the NVhost read module regs return error and free the kmalloc buffer and read error. The while loop, we break the while loop. So after we overwrite the kmalloc buffer, we can set one big value to the offset, and it will get get the big offset from user space, and pass the offset to NVhost read module regs, and then break the while loop. So this method will solve the infinite loop problem. So now, shortly summarize what we have. We have an integral flow bug. This integral flow bug can change to heap buffer overwrite, and the heap buffer size we can control the heap buffer size because we can control the block size multiply the number of sets. We also can control the heap buffer overwrite length because we can control the offset. You can see we set the block size to 4, and each time overwrite 4 bytes and set a big offset to break, so we can control the overwrite length. the overwrite content we may have a chance to control because we can write values to the register first and read out from it. But we need to do an experiment. So I do this. I write many magic number to register and read them out, and to do this operation several times. And what I found are like this. The memory layout read out from register is the same each time. Value in some fixed offsets is always 0. Value in some other fixed offset is always the magic number we write to. And value in other offsets is some random value. The memory layout is like this. We write a magic number to the register and then read out. We found in some offsets it's always the magic number we write, and in some offsets it's always 0, and other offsets is some random value. So now what do we have? We have a heap buffer overwrite bug. Heap buffer size we can control. We can control heap buffer overwrite length. We also can control the overwrite content. We can overwrite 4 bytes 0 or 4 bytes the magic number. We can specify the magic number. So what's the next? Overwrite. What object we should to overwrite? There are 3 choices. The first choice is function pointer. We can overwrite a function pointer to, for example, a user space function pointer, and if on 32-bit Nexus device, this is okay, because on 32-bit device, SMEP or PXN is not enabled. But Google Nexus 9 is 64-bit device. The SMEP is enabled, so this is not a good choice. The second choice is overwrite an object point. This object contains a function point. This choice is good because SMAP is not enabled on even 64-bit Nexus device. But this choice need ROP to root, because you can't directly read or write the kernel memory. You need ROP to do the read and the write. The last choice is the struct thread info. This is the best one because we know there is an address limit field in the struct thread info. If the address limit is a very big value, means that user space can access kernel memory. If we overwrite the address limit to -1, the user space thread can read and write arbitrary kernel memory directly. This is the best one because this choice doesn't need any ROP. So how to overwrite the struct thread info? This is the definition of the struct thread info. What we have now. We can control the overwrite length. So we can only overwrite 16 bytes. And we can control the overwrite content. Each time 4 bytes, the 4 bytes should be 0 or other specified number. So we can overwrite the flex field to 0 and overwrite the adjust limit to -1. We can achieve this by our bug. So if I want to overwrite the thread info, I want this kind of memory layout. I want the kmalloc buffer just in front of struct thread info, and then we just overwrite 16 bytes to corrupt the next struct thread info. So this is my plan. First, I create many threads. It will spray many struct thread info on the heap, on the kernel heap. And after threads created, I begin to free some of these threads. At the same time, another thread triggers the bug to kmalloc buffer and overwrite 16 bytes out of the buffer. First 8 bytes set to 0, and the second 8 bytes set to -1. The kmalloc buffer will occupy the freed memory of one struct thread info. After doing this, each live thread, check if it can read kernel memory directly from user space by a trick. We use a pipe to test. We read from pipe. If one thread can read kernel memory directly in user space, means that we find the corrupted thread info belongs to this thread. This is the memory layout changing. Firstly, I spray many struct thread info on the heap by creating many threads. And then I begin to exist many threads. This will cause some struct thread info being freed. At the same time, I check the bug to kmalloc 16K buffer to occupy one freed struct info, and then overwrite 16 bytes to the next struct thread info. How can I assure the occupy success? Firstly, I spray big number of thread info. So thread info which are allocated lately, very lately, will be continuous because it occupies occupy almost all the heap memory. So the struct info allocated lately will be continuous. I only free few of them, and the freed struct thread info are allocated lately. And I don't free continuous thread info. Only 1 out of 6 continuous thread will be freed. We can check the pseudocode. This is the pseudocode. I spray the thread info. You can see I use pthread create to create many threads, and I save the TID of each thread in the TID array. After this these threads created, I notify each thread to check it needed free itself or not. So we can see this is the spray thread. Each thread will check the TID by comparing the TID array received, and we can see that the code check the index of the thread is bigger than the threshold or not, and only 1 out of 6 will be freed. If the thread still alive after the first signal, it will receive the second signal from main thread to check if it can read kernel address directly by using read pipe. If read kernel memory is successful, then we get the corrupted thread, which can read and write kernel memory. So if the read kernel success, we got the thread, and we can do read and write memory in this thread. So finally, we get the thread which can read and write kernel memory. We can get the address of init task and SE Linux enforcing by analyzing the kernel image, because there is no ASLR on Nexus device. I search from init task, because every task is linked into the init task. So I search from init task to get current task by reading kernel memory from user space. After finding the current task, we can change the create of current task. Before doing this, we need to disable the SE Linux enforcing. So after doing this, we root the Google Nexus 9. So what about Tesla? I don't have a Tesla to test, but I know that Tesla is using Tegra 3 platform when I was browsing some search result of Tegra platform. It is something like Ubuntu plus Tegra 3. So I thought about that. Can I find some Tegra bugs without a car? So I searched Tegra 3 platform and found that Nexus 7 is based on Tegra 3 also. So I downloaded the kernel source code of Nexus 7 and audit the code, construct POC, and test on Nexus 7. Then I report I reported this bugs to Tesla and got some rewards. Easy. This is easy, okay. There is the demo. Sorry. Huh? I need some help. Oh, I have. I'll check this. How can I? I have a MP3. Sorry, this is the demo. Yes. Because it is with some time to spray the many threads. Root successful. Okay. And I would like to thank my colleague Hayden Xiao and Wish Wu. Thank you very much. Thank you for coming to my presentation.